Three shots in Dallas. The sun was high over Dallas, warm and bright, casting sharp shadows across the manicured lawn of Dealey Plaza. It was just past 12:30 p.m. on Friday, November 22nd, 1963. A crowd lined the streets, waving flags, holding children aloft, and craning their necks for a glimpse of the 35th President of the United States. And then he was there. Riding in an open-top Lincoln Continental, President John F. Kennedy smiled and waved, his young wife by his side in a pink suit and matching pillbox hat. Texas Governor John Connally sat just ahead of them, also waving, as the limousine turned slowly from Houston Street onto Elm. For a moment, it was picture perfect, an American leader basking in public admiration beneath a clear blue sky. Then came the first sound. Crack! Some thought it was a firecracker. Others flinched, startled by what might have been a car backfiring. The motorcade continued, hesitating slightly. Crack! Now screams, a flurry of movement. Governor Connally slumped in his seat. Secret Service agents turned, scanning the buildings, drawing their weapons. Crack! President Kennedy's head snapped violently. Red mist rose briefly into the sunlight. Chaos surged forward like a wave. The limousine accelerated. Jacqueline Kennedy crawled onto the trunk in desperation. A Secret Service agent leapt onto the car from behind. Onlookers shouted, ducked, ran. Cameras shook. The entire world, it seemed, stopped breathing for a moment and would never quite breathe the same again. In the aftermath, only one thing was clear. Three shots had been fired in Dealey Plaza, but from where, by whom, and in what order? The official story said a lone gunman, Lee Harvey Oswald, had fired from the sixth-floor window of the Texas School Book Depository, that he had squeezed off 3 rounds in under 6 seconds with a surplus bolt-action rifle, that he had missed once, then hit twice, fatally. Yet something about that story felt off. How could a man miss his first and closest shot, only to land a devastating headshot moments later? How could a moment of such precision begin with such failure? For decades, these questions echoed louder than the gunfire itself. Conspiracy theories took root. Trust in institutions eroded. The truth, obscured by layers of doubt, slipped further into shadow, until one physicist, armed not with theories or agendas, but with math and a 3D model of Dealey Plaza, asked a new question. What if the answer wasn't in who fired the shots, but in the angles between them? As the echoes of that final shot faded into history, what remained was a case frozen in time, part tragedy, part mystery, and endlessly debated. For years, investigators focused on who had fired the shots, why they had done it, and whether someone else had helped. But there was another way to understand what happened, one that didn't begin with motives or conspiracies, but with measurements. One that didn't rely on speculation, but on the physics of space, motion, and sightlines. To truly grasp how the assassination unfolded, we must step back, not emotionally, but physically. We must rise above the crowd, look down at Dealey Plaza as it was, and ask, what would a sniper see? What would he track, angle by angle, second by second, as a moving target passed through his field of fire? This is where the story begins again, not with gunmen in the shadows, but with geometry in the light. Reconstructing the shots. Dealey Plaza has become a shrine of speculation. To walk its sloped lawns today is to step into a crime scene preserved in collective memory, forever paused at 12:30 p.m., November 22nd, 1963. Tourists stand near a white X painted on the street where the fatal shot struck. They look up toward the sixth-floor window of the Texas School Book Depository, trying to imagine what a lone gunman might have seen. But imagining isn't enough. If we want answers, we need to reconstruct the shots, not just narratively, but physically. This is exactly what physicist Nicholas R. Nalli set out to do, not as a conspiracy theorist or historian, but as a scientist. In 2018, Nalli applied a forensic method often reserved for traffic accidents and military targeting: three-dimensional modeling and angular tracking analysis. Using modern tools like Google Earth Pro and verified measurements of Dealey Plaza, he simulated the exact environment a sniper would have faced that day. What emerged was not a theory, but a pattern, one that reversed decades of assumption. For all the mystery surrounding the shots, Nalli's findings suggested a startling truth. The first shot, despite being closest to the target, was the hardest to make. The third shot, despite its horror and finality, was the easiest. This wasn't a contradiction, it was geometry. By modeling the sniper's line of sight and calculating how much angular movement was needed to track the limousine at different points along Elm Street, Nalli demonstrated how the perceived motion of the target changed dramatically depending on its position. As the limousine passed beneath the sniper's window and turned down Elm, it transitioned from a high-speed oblique target to a slow-moving or nearly stationary object from the shooter's point of view. The implications of this are profound. What had long been viewed as a suspicious firing sequence, miss, hit, kill, was not the result of luck or conspiracy, but of increasing target stability and decreasing angular difficulty. The final shot didn't defy logic, it followed it. To understand why one shot missed and another struck with fatal precision, we need to begin not with theories, but with a map and a rifleman's line of sight. From the sixth floor southeast window of the Texas School Book Depository, the sniper had a commanding view of Elm Street, which curved gently downward away from the building. This window, later dubbed the sniper's nest, was positioned at roughly 60 feet above street level and just beyond a live oak tree that obscured the street near the intersection with Houston. At first glance, this may seem like a crude vantage point, but Nalli's reconstruction revealed otherwise. When he digitally recreated Dealey Plaza in Google Earth Pro, complete with 3D building models and street grids accurate to modern survey standards, a striking truth emerged. The sniper's nest offered the clearest, most stable firing lane available in the plaza. Why? Because it minimized what marksmen call angular tracking, the degree to which a shooter must pivot their weapon to stay locked onto a moving target. This is crucial. Hitting a moving object doesn't just depend on distance, it depends on how much the target shifts across the shooter's field of vision over time. Imagine standing still while a car drives past you from left to right. You have to turn your head rapidly to follow it. But if that same car is driving directly away from you, it barely moves in your visual frame. This is the principle of angular motion, and it was central to Nalli's analysis. Using the Zapruder film to identify the approximate locations of the limousine during the three shots, commonly believed to be 1. The first missed shot just after the limousine turned onto Elm. 2. The torso shot, striking both President Kennedy and Governor Connolly. And 3. The fatal headshot as the limousine neared the triple underpass. Nalli calculated the angular tracking speed for each. The results were astonishing. These numbers revealed a geometric paradox. The closer the target was, the harder it was to hit. The limousine, as it passed directly below the window, moved fastest across the sniper's field of view, making aim acquisition and tracking far more difficult, especially through a telescopic sight, which narrows a shooter's peripheral vision. By the time of the third shot, however, the car had moved far enough down Elm Street that from the sniper's perspective, the target appeared to be gliding almost straight ahead, angularly slow, stable, and predictably aligned. This is why, in a tragic twist of physics, the final shot was the easiest. Not only did the angular motion decrease dramatically, but the sniper had time to reset his position, stabilize his aim against the stacked boxes in the window, and fire at what had become, for all practical purposes, a nearly stationary target. To move beyond theory and into verifiable truth, Nicholas Nalli turned to mathematics, specifically Euclidean geometry. His goal was to calculate how much angular tracking required for a sniper positioned at various points around Dealey Plaza, particularly the sixth floor southeast window of the Texas School Book Depository. What made this analysis so innovative wasn't just the method, it was the fact that it treated the assassination as a physical event with measurable variables rather than a mystery shrouded in narrative. At the core of the analysis was a simple geometric concept: the tracking swath, or the angular area through which a shooter must pivot to follow a moving target. Imagine this as a triangle. The base of the triangle is the stretch of Elm Street that the presidential limousine traveled between two shots. The other two sides are lines of sight drawn from the sniper's location to the beginning and end of that stretch. The angle between those two lines, the apex of the triangle, is the critical measure. It tells us how much the shooter had to rotate his rifle both horizontally and vertically to stay aimed at the moving target. To get precise data, Nalli used high-resolution satellite and 3D topographical data available in Google Earth Pro, ensuring that distances and angles reflected the real-world layout of Dealey Plaza. Using points and known locations of the limousine during the three shots, he constructed three key triangles and applied the law of cosines to solve for the tracking angle. These tracking angles not only align with known locations in the Zapruder film, but also reveal a consistent pattern. The sniper's job got easier with each shot. In practical terms, a tracking speed of 7.63 per second, as in the first shot, is considerable, especially when using a fork-eye magnified scope. That amount of angular movement is roughly equivalent to following a fast-moving bird with a camera lens while standing on a rooftop. The chance of missing is high. By contrast, the final shot occurred when the limousine's angular motion had slowed to a near glide. At 1.1 degrees per second, the president's head presented a tragically still and centered target, made easier still by the gun rest built from cardboard boxes within the sniper's nest. Perhaps most compelling, this model not only confirms the viability of the lone gunman theory, but rationalizes the exact order of events that has puzzled investigators and the public alike for decades. There is no need to invoke mystery when physics offers a consistent, repeatable explanation. To test the robustness of his findings, Nalli also ran the same calculations from other sniper locations proposed over the years, such as the Daltex building, the grassy knoll, and the southwest window of the book depository. None matched the southeast window in terms of offering both concealment and a shallow, stable tracking swath. For example, grassy knoll required 33.5 degrees of angular tracking with exposed visibility and no recovered physical evidence. Daltex building, 10.6 degrees of tracking, but with serious visibility issues and no line of sight before the oak tree. TSBD southwest window, 20.1 degrees of tracking, nearly triple the difficulty of the actual sniper's nest. These results only strengthen the conclusion the sixth floor southeast window wasn't just a convenient place to hide a rifle, it was, geometrically and logistically, the optimal location to carry out the assassination. How history got it wrong. If geometry made sense of the assassination, it also exposed how easily the human mind resists it. In the aftermath of President Kennedy's murder, the United States government scrambled to provide clarity to a shocked and grieving nation. Within a week, President Lyndon B. Johnson appointed the Warren Commission to investigate the killing. Composed of high-ranking officials, including the Chief Justice of the Supreme Court and the former director of the CIA, the commission had access to the full resources of the federal government and an unspoken mandate: settle the public's fear. But the Warren Commission didn't have access to modern forensic modeling, 3D simulations, or angular tracking calculations. It operated under the limitations of the 1960s, relying on static photographs, human recollection, and an emerging but incomplete understanding of ballistics. More importantly, it carried with it a critical assumption: one that would shape its entire timeline and, ultimately, its conclusions. That assumption was this: the first shot must have hit. To the commission, it seemed implausible that a Marine trained marksman would miss his first and closest shot. If a shooter had a clear view of the president at such a short distance, why would he fail? Rather than exploring the mechanical reasons behind a possible miss, the commission built its case around a sequence in which the first shot struck either President Kennedy, Governor Connolly, or both. This decision had a cascading effect. To fit the three-shot scenario into the roughly 6 seconds of firing time recorded in the Zapruder film, the commission placed the shots tightly together. Shot 1 hits, shot 2 is the so-called magic bullet, and shot 3 delivers the fatal head wound. But by assuming the first shot landed, the commission left no room in the sequence for a miss, despite eyewitness reports, physical inconsistencies, and the absence of a clearly identified first bullet impact. The result was a timeline that felt forced. The spacing between the second and third shots, just over 1.5 seconds, seemed implausibly fast for a shooter using a bolt-action rifle with a telescopic sight. Expert marksmen in FBI and Army tests struggled to replicate the timing with consistent accuracy. The commission's response was to imply exceptional skill on Oswald's part, but even that didn't explain the odd sequence of hit, hit, kill. In truth, what felt implausible wasn't the shooter's performance, it was the narrative wrapped around it. And that narrative, as Nicholas Nalli's angular tracking model later showed, was based on a flawed understanding of shooting geometry. If the commission had considered angular velocity, how fast the limousine was moving across the shooter's field of view, it might have reached a different conclusion. The first shot, far from being the easiest, was the most complex, requiring the highest degree of motion tracking. The third shot, long considered miraculous, was actually the most stable. But in the absence of that knowledge, the commission built a timeline that didn't quite fit the evidence, and in doing so, planted the seeds of doubt that would grow into a forest of conspiracy. When Abraham Zapruder captured 26 seconds of film on that sunny Dallas afternoon, he unknowingly recorded the most scrutinized footage in American history. The Zapruder film provided a frame-by-frame visual record of the assassination, allowing investigators to count frames between shots and synchronize visual data with audio testimony. The Warren Commission relied heavily on this footage to construct the shooting timeline, determining that the three shots were fired within a span of about 5.6 to 6 seconds. But while the film offered timing, it lacked dimension. It showed where the limousine was, but not how it was moving relative to the shooter's field of vision. It revealed reaction times and impact moments, but not the tracking complexity each shot required. In 1964, investigators lacked the tools to render a three-dimensional analysis from the film. There was no way to model angular velocity or simulate sniper sight lines. As a result, the film became a visual anchor for a linear timeline, but not a geometric one. It contributed to the false assumption that proximity equals ease, and it obscured the fundamental truth revealed decades later, that motion matters more than distance. What the Zapruder film could have shown, if paired with 3D modeling, is that the first shot occurred at a moment of maximum angular difficulty, while the third occurred during maximum angular stability. But in 1964, that insight remained invisible. Dealey Plaza was filled with people, dozens of them within earshot, many with a direct view of the limousine. Their statements were detailed, sincere, and often wildly contradictory. Some said the shots came from in front of the car. Others swore they came from behind. A few claimed to hear 4 shots. Some reported near simultaneous bursts, while others described clear spacing between the gunfire. Some recalled Kennedy reacting to the first shot. Others said he didn't flinch until the second. Faced with a chorus of conflicting memories, the Warren Commission leaned heavily on consistency, favoring testimony that fit a coherent timeline and dismissing outliers as confusion or error. This was understandable, but it was also limiting. The Commission treated inconsistencies as problems of memory, rather than recognizing them as reflections of geometric and acoustic variation. From different vantage points across the plaza, the same event could and did look and sound different. Echoes off buildings, the layout of the streets, and the angle of the limousine's path all contributed to an experience that was highly location dependent. Had investigators cross referenced these perceptions with a 3D model of Dealey Plaza and used sound mapping or visual triangulation, they might have recognized a key truth. The physical environment shaped what people heard and saw, not just their memories. But that method lay decades in the future. The third major weakness in the Warren Commission's investigation lay in its treatment of ballistic evidence, particularly the so called magic bullet theory and the missing physical trace of the first shot. The commission concluded that one bullet passed through President Kennedy's upper back, exited his throat, entered Governor Connolly's back, fractured his ribs and wrist, and lodged in his thigh. This bullet, later recovered nearly intact on a hospital stretcher, was said to have caused 7 wounds across 2 men. To critics, this theory strained credulity. The bullet's near pristine condition and complex trajectory fed public doubt. But the real weakness wasn't in the damage it caused, it was in the assumption it was the first shot, because no one could locate a bullet impact from a clear miss. No damage to the limousine, no fragments embedded in pavement. The commission hesitated to acknowledge that a shot might have gone wide. In doing so, they boxed themselves into a timeline that required every bullet to count and every shot to hit, or at least to leave forensic evidence. Later research, however, would suggest that a missed first shot might have struck a traffic light pole or ricocheted from the curb near James Tague, a bystander who was slightly injured by a fragment. But by then, the Commission's official story had already been written. Had they incorporated angular tracking into their analysis, they may have realized what Nalli would later prove. The first shot was geometrically the most difficult, and therefore the most likely to miss. Accepting that possibility would have relieved the timeline and allowed the remaining 2 shots to be spaced more plausibly, even within the constraints of Oswald's bolt-action rifle. In its final report, the Warren Commission offered a conclusion that was both definitive and uncertain, that Lee Harvey Oswald acted alone, firing 3 shots from a 6th-floor window with deadly effect. And yet, in its construction of that timeline, in its reliance on assumptions over physics, witness preference over environmental modeling, and a need for coherence over complexity, it sowed doubt instead of settling it. The commission did not lie, it simply lacked the tools to see what could not yet be measured. Had investigators asked not just when and where, but how, had they considered that geometry might explain what intuition could not, the narrative might have been very different. They might have seen that a missed first shot wasn't a failure, but an inevitability, that the so called miracle shot was, in fact, the most physically manageable, that the 6th-floor southeast window was not just a perch, but a mathematical advantage. Instead, history accepted a story that felt uneasy and incomplete. That unease gave rise to conspiracy, not because the truth was impossible, but because the explanation was implausible. In time, though, a new approach emerged, one not based on testimony or theorizing, but on calculation, a method that asked Dealey Plaza to speak for itself through lines, angles, and measurable motion. Where history erred, science stepped in. And so we now turn to a different lens, not to re-argue the case, but to reconstruct reality as it actually unfolded, second by second, degree by degree. The truth, it turns out, was never lost. It was just waiting to be measured. For decades, the assassination of President John F. Kennedy has hovered in a realm between history and myth, more analyzed than understood, more narrated than known. What gave this tragedy its staying power was not just the enormity of the loss, but the lingering sense that something didn't add up. That the story we were told about three shots, a lone gunman, and a moment frozen in time somehow defied belief. And in a way, it did. But not because it was false, because it was incomplete. The original investigation asked the right questions: who, when, how, but tried to answer them without the tools to model motion, measure angles, or simulate a sniper's view in real space. It confused distance for difficulty, testimony for geometry, intuition for fact. Then came the science. What Nicholas Nalli's reconstruction revealed was simple and profound. The sequence of shots that once felt improbable was, in fact, the most mathematically likely. The missed first shot was the hardest. The fatal third shot was the easiest. Not because of luck or magic, but because of declining angular motion, sniper advantage, and the cold logic of trajectory. This is more than a forensic breakthrough. It is a reminder that the past is not beyond reach, that with the right tools, we can revisit even our most shadowed moments, not to rewrite history, but to sharpen it, to let truth rise not from what we remember, but from what space and motion remember for us. There will always be mysteries. There will always be doubt. But in an era clouded by misinformation and polarized belief, the value of clear, measurable truth cannot be overstated. Science may not answer every question, but it offers something just as powerful: a way to separate the improbable from the impossible and the plausible from the invented. We owe it to history, not just to record what happened, but to understand how it happened. Sometimes that understanding comes not from new witnesses, but from new methods, not from louder arguments, but from quieter calculations. In the end, the story of the Kennedy assassination is not just about a nation losing a leader. It's about how we learn to find clarity after the chaos. And sometimes the clearest answers come not from the words we speak, but from the angles we measure.